Emergent SU for symmetry in a quantum spin-orbital.
Thank you for the introduction, Gregor. I'm Masahiko Yamada from the Institute for Solid-State Physics, the University of Tokyo. First, let me thank the organizers for inviting me and giving me an opportunity to presenting my work here. I was surprised to find that my talk is the only one including materials name here. And it was most difficult to make these three small in the title of my talk from the program. I first asked Gregor to make this small, but he didn't know how, so I had to ask Carolina to change the title of my talk from the program. Okay, let's begin from the outline of my talk. First, let me introduce the notion of quantum spin-orbital liquids, and then I will move on to the main topic which is just the material proposal for the new quantum spin-orbital liquid. And I derive the low energy effective model and show the existence of the emergent SU for symmetry in this model. Then later I will discuss the 3D generalization, etc., and then summarize my talk. Let me begin from the introduction. And as already introduced by Carlo in his talk, and nowadays people are interested in frustration coming from spin-orbital coupling. And especially interesting is the case where the interaction becomes so-called Kitaev type. Kitaev type interaction can be depicted like this. For this blue bond, we have a z-directional anisotropy in the spin interaction. And for the red bond, we have y-directional anisotropy. And for the green bond, we have x-directional anisotropy. In this case, this interaction is called Kitaev type. And in this interaction, we can strongly frustrate the system even on the honeycomb lattice. And this type of frustration is also called exchange frustration, and it is known to be realized in materials like iridates or ruthenium compounds with strong spin-orbital coupling. What happens can be understood in this way, and the spin-orbital coupling usually reduces the symmetry of the spin space from SU2 to the point group. And in this way, we can, for example, reduce the interaction from Heisenberg to this sigma z Ising type interaction. And from the point group, we can prove that this always reduces to this type of Kitaev type interaction on the honeycomb lattice. So Jacquet-Carré actually proves that this type of interaction arises when we take the strong spin-orbital coupling limit. And this type of frustration owing to the spin-orbital coupling is nowadays very attractive. And the nice thing about this Kitaev model is that this model on the honeycomb lattice is actually exactly solvable. So we can try to compare the theory and the experimental results for iridates or other ruthenium chlorides. So in this sense, this is a very exciting field, both from the experimental and theoretical point of view. On the other hand, the quantum spin-orbital liquid is a bit more, complicated situation. And already known candidate for the quantum spin-orbital liquid is a famous honeycomb like barium kappa antimony oxide, which was synthesized in Nakatsuji group in ISSP. And this material has a kappa 2 plus ions in the octahedral coordination. In this case, both spin and orbital degrees of freedom are actually active, and we have 2 times 2 equals 4 states per site for each kappa 2 plus site, forming this honeycomb type lattices. And this material is nice in the sense that we know that both spin and orbital degrees of freedom are active at low temperature. In this sense, we can call not just a quantum spin liquid, but rather quantum spin orbital liquid, where we observe no magnetic order or spin freezing at lowest temperature. Not only that, but also we observe no Yan-Taylor distortion or orbital freezing at lowest temperature. And in this sense, this material is experimentally very nice and interesting. But the problem here is that if we write down the effective model for this kappa size, then the spin orbital model becomes this complicated form. So the problem is that we cannot compare these nice experimental results to any solvable or analytically tractable model. This is too complicated to treat in a theoretical way. So that is a problem from theorist's view to discover whether this ground state looks like or spectrum looks like. So in this sense, it's still difficult to treat directly this material. So we need another material, another canonical candidate material for this quantum spin orbital liquid state. Okay. We just skip this slide for time. But simpler model to treat this type of quantum spin orbital liquid physics with 2 times 2 states per side is a SU2 cross SU2 Kugel-Komsky model with 4 states per side. And if you write spin degrees of freedom as SI operators and orbital degrees of freedom as TI operators, then the Hamiltonian can be written by these 2 spin half operators for 4 states problem. And for example, assuming the SU2, which is for the spin space, and SU2 orbital space symmetry for both spin and orbital degrees of freedom, the Hamiltonian can generally be written as this Heisenberg-like form. And in this form, we can not only the spin-spin interaction, but also we can treat the spin-orbital interaction from the cross term of these 2 terms. Then we can seek for interesting physics where spin and orbital both degrees of freedom are entangled. So it's a too simple or simplified model for this problem, but still interesting and well studied in the theoretical physics point of view. And even more interesting is there's a nice point for these C1, C2 parameters where we can actually enlarge the symmetry from SU2 cross SU2 to SU4 symmetry. And this special point is called SU4 Heisenberg model or SU4 Heisenberg point. And this is actually written by the exact point that C1 equal 1 over 4, 1/4, and C2 is also 1/4. At this exact point, at the phase diagram of this C1 and C2, and we can actually show that this special point has a enlarged SU4 symmetry. And in this sense, we can call this model as SU4 Heisenberg model. And from the due to the enlarged symmetry, this model is actually numerically or analytically more tractable. And there are some theoretical works for this SU4 Heisenberg model as a kind of canonical example of quantum spin orbital. And especially interesting in the case of the honeycomb lattice, which was discussed in this Philip Colport's and Frederick Miller's paper on PRX. On this paper, they are calculating variational Monte Carlo or IPEPs of the this SU4 Heisenberg model on the honeycomb lattice, and they suggest that the SU4 Heisenberg model honeycomb lattice hosts quantum spin orbital liquid with this pi flux Dirac dispersion, and in this sense, they conclude that this model actually shows a quantum spin orbital liquid nature with Dirac spin liquid dispersion. At least theoretically, this is only one established example of quantum spin orbital liquid with fractionized excitations and with a finite stability window actually shown. It's too small, but there's actually a small spin liquid region here, which is actually finite.
Remember what other parameters?
Probably, in this case, probably the further neighbor interaction J2 or J3, I guess, if I remember correctly. Okay. That's what we already know for this model. And my talk in the later section is mostly on the physical realization for this model, which actually exists in real material. And from going to the main topic, I will briefly discuss why this type of enlarged symmetry like SU4 can promote spin liquid or spin orbital liquid states. And we can expect two effects from the enlarged symmetry. First of all, quantum fluctuation is known to get stronger in SUN or large symmetry case. It's simply understood by considering the classical ground state manifold. If you only consider the SU2 or kind of Ising type spins, then for the anti-ferromagnetic interaction, we only have two degenerate classical ground state, only net states up, down, up, down, down, up, down, up, down. So only we have two degenerate states for at least 1D chain. 1D chain. On the other hand, and SU4, even for the 1D chain, we have more candidates, ground state, classical ground state, AB, 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 ABC, 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 ABCD, ABCD. If we consider this ABCD as 4 flavors of the fundamental representation of SU4, then we have larger classical ground state manifold. So we can consider the more, how to say, superposed entangled quantum ground state for this macroscopic number of degeneracy. So at least in this simple picture, we can expect that generalized SU4 or SUN spin systems has more fluctuation, but it's only for the, how to say, not large n, just moderate n. And also, other interesting points of view is coming from the extension of Lipschitz-Matisse theorem. If we consider Lipschitz-Matisse condition for the SU2 system, the honeycomb lattice is known to be very trivial, or how to say, the honeycomb lattice is regarded as unfrustrated lattice. But this is because SU2 Lipschitz-Matisse condition only considers the even or odd sites per unit cell, even or odd spins per unit cell. But if we consider SU4 symmetry, the important thing to get the trivial singlet ground state is whether there are multiple of 4 spins or sites per unit cell. So from this difference, the honeycomb SU2 model can be trivial, simply be trivialized because we can form a singlet inside the unit cell. But in the case of SU4, we cannot construct a how to say, SU4 singlet inside the unit cell because we need 4 fundamental representation to construct a singlet SU4 representation. Okay.
About this SU4 symmetry, so what is the third considered quantity? You have SZ and TZ, and what's the third one?
It's not simply be written here, but we basically have 3 SU2 inside SU4, and as he said, charge is 3 charge. Yeah. We have at least 3 charge, and also some complicated algebra for this guy. These things we can simply discuss from the Lipschitz-Matisse, and we skip this slide, but I how to say, quickly summarize the SEN extension of the Lipschitz-Matisse theorem here for your information, and we later call this SEN generalization of the Lipschitz-Matisse theorem as Lipschitz-Matisse-Affleck theorem. And this is the end of the introduction, and I will move on to the main topic of the material proposal for the SU4 models. Okay. Then from now I will move on to the material side, and I will begin from the D1 electronic configuration to realize SU4 systems. D1 electronic configuration has only 1 electron inside the d orbitals, and d orbital is 5-fold degenerate. But if we include the octahedral Ligand field of the material, which will split to the 2 and 3, and we only consider the lower manifold with actually 6-fold degeneracy, including spin degrees freedom. And additionally, if we include the spin of the coupling in the form of L dot S, then this 3-fold degenerate so-called T2G manifold splits into 2 and 4 degenerate states. And the upper 2 is the famous J equal 1/2 doublet, and the lower one is called J equal 3/2 quartet. And in this case, it's D1, so we only have 1 electron in the lower one, so we will concentrate on this 4-fold degenerate J equal 3/2 state, which we write as psi vector. And this has 4-fold degeneracy and J equal 3/2 magnetic moment. And this state will be realized in titanium 3 plus or zirconium 3 plus or hafnium 3 plus, and which actually has D1. And if we increase the atomic number from titanium to hafnium, then we can increase the strength of spin-orbital coupling. Then this lambda goes infinity, and this J equal 3/2 picture would be exact in the heavier case. So in this large lambda limit, 6-fold degenerate D1 ground state splits into these two states, and we regard this J equal 3/2 4-fold degenerate states as a ground state manifold. Okay. And there actually exists a very nice material called α-ZrCl₃, which was reported 50 years ago. And this was synthesized by chemically from zirconium tetrachloride to zirconium trichloride. And this α-ZrCl₃ trichloride actually has this nice honeycomb structure with octahedral coordination. And also we have it's a 4D metal, so we can consider strong spin-orbital coupling enough in this material. And the physics very looks similar to alpha ruthenium chloride candidate, type candidate, and the structure is almost the same, and both has a honeycomb layered structure, and also octahedral coordination of the chloride. So we can start beginning from the almost the same multi-orbital Hubbard model as the alpha ruthenium chloride, but the difference lies in the projection. In the case of ruthenium chloride, we project the multi-orbital Hubbard model onto the J equal 1/2 subspace. But in this case, in our case, α-zirconium chloride, we will project the Hubbard model onto the 4-fold degenerate psi J equal 3/2 quartet, and then we will derive the effective 4-flavor Hubbard model inside this physical ground state. Okay, in this way we can construct the 4-flavor or 4-state Hubbard model in this way, and we just write psi as the spin-orbital vector of the with the 4 component, and we omit the indices for this 4 component for simplicity.
Sorry, can you repeat how many electrons do you have?
So electrons what filling?
Yes.
We have 4 states per site and only 1 electron per site, so quarter filling is exactly at quarter filling. Okay. So we want to construct the fundamental representation. So and if we correctly project out, then you can simply see the Hubbard interaction actually has a simply SU4 symmetry exactly. And the problem lies in the hopping term. And the hopping term is not just a C number, but rather there's a, how to say, matrix of diagonal element, which is written here in the form of 4x4 matrix. So the problem is, although this Harvard model currently has a SU4 symmetry, the hopping term now breaks the, seems to break the SU4 symmetry by this exotic, complicated hopping matrices. So we need something, but interestingly, if we focus on the how to say algebraic property of these U matrices, we can easily see that if we calculate the flux or product of the 6 matrices, hopping matrices coming from A, for the hexagon from here to here to here to here to here to here to here, and multiply these 4x4 matrices 6 times in this way, then we can actually get that the product of this honeycomb loop becomes minus identity matrix. So in this way, actually we can see that the flux in the sides of honeycomb bracket is actually just abelian. And from this relation, we can find a gauge transformation, making all the hopping matrices to the abelian component. And the gauge transformation is something, just a base transformation for each side, like this. And from this condition, we can actually exactly directly find the gauge transformation with the condition where the transformed Uij matrices becomes abelian. And such a gauge transformation is simply finding 1D without any condition, because we can just doing the gauge transformation one by one to eliminate all the flux component by changing the bases one by one from left to right. But in the case of 2D, we have a flux inside this room, so we need a flux condition to actually find the gauge transformation. If we consider the open boundary system, then we can first do the 1D gauge transformation for this red, red snakes. Then we can simply make this all the red bonds to identity by the 1D gauge transformation. And additionally, from this constraint, which is invariant under the gauge transformation, from the flux condition, the product of the 6 matrices around the bracket has to be minus identity. So we can actually prove just making this red bonds identity, or the bond becomes identity or minus identity, depending on the flux condition. In this way, we just left with a completely abelian SU for Harvard model, but with this plus minus phase factor here as a eta Ig. This is nothing but a so-called pi flux SU for Harvard model on the honeycomb lattice. And since the gauge transformation keeps the flux inside the bracket, the unit cell is effectively doubled with plus identity bond and plus minus identity bond. But in this way, the global SU4 symmetry becomes completely explicit, and in the transformed basis, except for this eta Ij, it is completely the complete SU4 symmetric Harvard model. So it looks nice, and which is better? Of course, this pi flux itself is something interesting, because it corresponds to a very large magnetic field if we regard this pi flux as simply coming from the Aharonov-Bohm effect. And if we calculate in this geometry, it is actually correspond to the magnetic field about 6,000 Tesla, which exceeds the world's record about 1,000 Tesla in a 6 factor. So in this sense, the pi flux itself is interesting, but more interesting is its its phase diagram. And from the free U equals 0, we just have actually a Dirac cone, and we already know that in the U infinity limit, it will go to the SU for Heisenberg model, which we know to be a Dirac spin rigid. So the phase diagram from here to here is already something interesting, but we don't know the nature of the transition because we only know only this limit or exactly solvable point. And the U infinity limit is simply becomes the SU for Heisenberg model as we first shown in the introduction section. And since the electron is a quarter field, this Hubbard model can be mapped to the SU for Heisenberg model in the large U limit simply just by the second order perturbation. But in this second order perturbation, the flux sector does not matter. So the plus minus factor disappears in the Heisenberg model. However, of course, in the 6th or 8th order, we get the flux-dependent term here. Of course, in real materials, we expect the U is much larger than hopping. So basically, we can expect that the physics of the α-zirconium chloride can be treated by this simple Heisenberg model. And from this point of view, we have proven that actually the low energy effective model of the α-zirconium chloride becomes this nice SU for Heisenberg model already studied by Philip Colbert. And from numerics, we already know that it would be a candidate for the quantum spin-orbital. In this sense, we find the new candidate material for the SU4 models and also the quantum spin-orbital liquid.
So there are plenty of examples, solid-state examples of having two orbitals in the field, but in most cases, you don't have any SU2 symmetry in the orbital sector due to absolute coupling and so on. So what is your approximation in deriving that Hubbard?
What is the approximation? One important approximation is actually ignoring the Hund coupling, JH, which is expected to be smaller than Hubbard interaction, but of course not how to say, one that's smaller than Hubbard, but not that small. And if we include the Hund coupling, then the actually, as you said, the symmetry between the yes. This is one approximation. Okay, if there is no problem, I will go on to the generalization of my work. And we only consider here in the honeycomb lattice, which actually we have a nice material. But rather, we can consider, how to say, imaginary or fantasy material with a more complicated structure with a 3D generalization of honeycomb lattice. The 3D generalization of honeycomb lattices are called 3D tricoordinate lattices, and there are many 3D variants of these lattices, but these lattices are classified by who? AF wells and also listed in this website of Maria Helmut. So we just check the such if this type of lattice, assuming this lattice exists in reality, then whether the SU4 is how to say. We check whether SU4 models appears or not. There are some conditions to get the SU4 model. We have to get a how to say. We have to have a gauge transformation to make the model to SU4 symmetric. Make the model SU4 symmetric. So we have to check the property of the UIJ hopping matrices. If this UIJ hopping matrices obey sorry. We first have to prove that for all brackets or all elementary loops, we have to prove that the product of the UIJ matrices has to be abelian. So we use this Majorana-like anti-commutation relations of these U matrices depending on the direction. And simply, for example, if we have a x-directional bond, then we can put just a ux, and this ux actually something like Majorana creation or annihilation operator, and we can simply use this algebraic relation to calculate the product of the U matrices around the loop. Then we can simply conclude that if the same color or if the same direction appears even times in each loop, then the flux becomes abelian, because it's just a Majorana creation and annihilation. We can regard this multiplication of U as a Majorana creation and annihilation. And honeycomb and some 3D lattices actually obey this condition. And then we can prove that there exists a SU4 symmetry also in these 3D lattices. And but something we have to check is how we use the anti-commutation relations determine the flux sector 0 pi. So if we want to know the flux sector, we have to do the calculation by your hand. This okay.
I'm confused with this biaxed conditions. I mean, of course, if this is satisfied, you will get an SU4. But you can just think about that you have some. I mean, you start from your ideal SU4 Hubbard model, where all the hoppings are diagonal, and suppose that you are turning your head randomly around, and then those U matrices that describe the randomly turned coordinate, I mean the hopping in these randomly coordinate things, they will be just essentially random. So you will not satisfy this anti-commutation relations.
Sorry, still I cannot get to your point, but
I mean, these conditions
okay.
are probably sufficient, but not necessary. So maybe these are necessary. I think what you say here is too restricted.
Okay.
You can have arbitrary, I mean, much bigger choice of U alpha, U betas, when you still end up with an SU4 model.
So you're saying even if you don't satisfy Majorana-like anti-commutation relation,
yes,
it's still possible to have zero flux?
Yes, yes, yes.
Yes, of course, but if we have for example, if we place the zirconium and the chloride in this form, I'm not sure it's possible, then the hopping matrices becomes always the same thing in this honeycomb lattice. And actually this UA and UB and UC obeys this anti-commutation relations. If you can, it's difficult to check, but you can simply calculate the UA and UV and compare with UV and UA. Then
Yeah, right. But this is because that you have chosen a particular coordinate basis, and if you don't have this basis, then you would have some. I mean, you can in principle rotate your four-dimensional local Hilbert space randomly, and then the U alpha that connect on this bond and this bond, they will not necessarily commute.
that's what still I cannot understand. But we are just defining.
But
So you think the commutation relation would depend on the gauge?
yes, it depends on the gauge, and what is important that if you go around the loop, you get the identity plus minus 1.
No. Commutation relation doesn't depend on the gauge because we fix the gauge by taking the one specific basis where I diagonalize JZ here.
Right, in this particular case, but I mean, it's not. Anyway, we can talk later about it.
So, sorry, I still cannot get your point, but let's take later.
Disagree. I think you are saying the same.
Okay. Again, these are examples. There are many 3D generalization of honeycomb lattice, and one example is hyperoctagonal lattice. And in this case, all of the for any loops we get the zero flux if we calculate directly the product of UIJ matrices. In some cases, similarly to honeycomb lattice, for example, in this complicated lattice, we get the pi flux in some octagon. This is a bit exceptional, but similar to the honeycomb lattice.
The first example has zero flux everywhere. That's what you say.
Sorry?
The upper example has zero flux everywhere.
Zero flux everywhere. And also, this can somehow justified from the symmetry arguments. Okay. Okay, and the problem for considering the SU for Heisenberg model on these 3D lattices is one thing is the lattice is too huge, and the other point is, for example, on this hyper-octagon lattice, the integral actually includes 4 sides, so we cannot use the conventional SU for Lipschitz Matisse Affleck arguments for this lattice. So we can get a very trivial state by constructing a singlet by anti-symmetrize all the 4 sides per unit cell to get a very, very trivial atomic state. But nice thing is we still have another symmetry which can actually protect the gapless or ground state degeneracy, which is called non-symmetric symmetries. And most materials actually has this non-symmetric element in the space group. And actually, the hyperoctagon lattice has a square axis inside the square spirals and also a glide mirror plane. So this square glide works very well to protect the quantum spin-orbital liquid. And the nice thing for this non-symmetric symmetry is differently from the symmetric operation. The integral B can be effectively reduced by dividing this non-symmetric symmetry. Non-symmetric symmetry is like this glide symmetry. If we have a foot here, then we have a reflection of the foot here with translation. Then the naive unit cell includes 2 feet, but if we divide this glide reflection, if we divide this naive unit cell by this glide reflection, we only have 1 foot for only left one included. So if we reduce the number of sites per unit cell by this division, we can extend the condition of Lipschitz-Matisse or Lipschitz-Matisse theorem, and we can prove that how gapless phases can be protected by this non-symmetric symmetry. This is following the Watanabe-san's discussion between this PNAS paper. And actually, I listed some of the 3D generalization of the honeycomb lattice and checked whether the extended or non-symmetric version of Lipschitz-Matisse theorem protects the quantum spin-orbital liquid or not. And we have listed check here. If we have a check, for example, for this hyperoctagon, in this case, we have a nice this type of glide mirror or skew symmetry, which can actually protects the ground state degeneracy or the gapless spectrum owing to the non-symmetric extended Lipschitz-Matisse theorem. And at least for these 3 lattices, hyperoctagon, hyperhoneycomb, 10-3D lattices, we already proven that the same argument for the honeycomb lattice applies even though the number of sites per unit cell is multiple of 4. Okay. So additionally, we named this new state quantum, not quantum, but newly we named this type of state crystalline spin-orbital liquid, assuming actually the hyperoctagon, SU4 Heisenberg model on the hyperoctagon lattice is actually a quantum spin liquid. The notion of crystalline spin liquid is kind of newly defined as a spin liquid where the gapless point or ground state degeneracy is protected by the space group symmetry, and especially by the non-symmetric symmetry. In the same way, and assuming that they are all quantum spin-orbital liquid, the SU4 Heisenberg model on the hyperoctagon or hyperhoneycomb lattices can be called crystalline spin-orbital liquids because in this case, simply the Lipschitz-Matisse or extended Lipschitz-Matisse theorem can protect the ground state degeneracy or the gapless point due to this existence of non-symmetric symmetries. And in this sense, we believe that this is something new in the field of quantum spin liquid. Finally, let me discuss the experimental side of our proposal. First of all, the material itself, for example, α-ZrCl chloride has been synthesized 50 years ago. So, in principle, any measurements is possible, and especially interesting to observe the orbital excitations, or what we call fractionalized orbital or orbitalon, is a finite frequency ESR measurements done first by Nakatsuji group, and it is known to be a very good signature for the quantum orbital fluctuation. And I will not explain the detail of this experiment, but actually this finite frequency ESR can capture the fluctuation of the G factor, which directly related to the fluctuation between the degenerate orbital manifold. And also we can use NMR or μSR for spin excitations to see the fluctuation. So at least we can see the quantum fluctuation for both spin and orbital degrees of freedom at the low enough temperature by NMR and ESR or MESR. And our expectation is to prove the existence of the SU4 symmetry is if the typical time scales coincide between NMR for spins and ESR for orbitals, then this suggests accidental, coincidence in the energy scale of these two different degrees of freedom. And in this sense, we can indicate the symmetry between spin and orbital if we have the accidental coincidence between the two time scales. So that's one possibility or one suggestion to discover this new SU4 symmetry. And also other possibility is that SU4 symmetry may change some universality class of critical phenomena. And this is also some interesting possibility we should seek for the future experiment or future research. As a summary, we have proposed α-ZrCl₃ as a honeycomb candidate material for the SU4 Hubbard-Heisenberg honeycomb lattice. And also it's a candidate for the quantum spin orbital liquid. And especially the SU4 Heisenberg models are expected to host quantum spin orbital liquid on many lattices, so we found a new candidate, many new candidates for the quantum spin orbital liquid. And this is just for the experimental suggestion, and especially finite flexion ESR will be important to observe the orbital excitations and also the symmetry between orbital and spin sectors, and that will be a signature for the SU4. That's all I have, and thanks for attention.
You showed some relatively simple U matrices.
Yes.
Can you explain again why they are so simple? What's the approximation?
There's no approximation actually. Just we can derive exactly if we start from this simple hopping model, and hopping model can be it's not enough, but written in the original for the original D64 degenerate T2G orbitals, we can write the hopping as in this way. This is a bit difficult to understand, but if we replace ABC to D, then this is just saying that the hopping is only by this chromium from XG, PZ, YZ, XG, PZ, YZ, PZ, XG, and this is what this tight binding model is saying. And if we simply project this 6-orbital tight binding model onto the 4-4 degenerate ground state, then simply we can derive this Hamiltonian. So one approximation is taking the kind of spin-orbital coupling to be large enough. In this approximation, we can derive it exactly.
So there was also a sketch of a possible phase diagram of the Hubbard model.
Yeah, that's a very rough because I don't know the intermediate.
Because you said the compound has been known for a long time. So, for instance, is it insulating or?
That's already a mystery because the only we know for this material, sorry, I made a mistake for this lecture. Only we know for this material is it's already synthesized in this material, and also they only take the X-ray, so we just only know the material exists and yeah, no evidence for insulating, so no magnetic measurements. Probably they are chemists, I guess. Okay.
Is it believed that the spin-orbital liquid would be stable to perturbations about the SU4 symmetric point, or would it just occupy a special point or an extended phase maybe?
That's a nice question. Actually, we know that this phase is stable in the SU4 symmetric perturbation, but if we break the SU4 symmetry, basically, I guess the not much is known for the stability. This would be nice to see in the future research.
What is the origin of the pi flux model? There's no magnetic field, so maybe your translation involves some spin rotation that effectively makes the translation to this magnetic translation.
I don't know. Yeah, we can simply say that the origin is a spin-orbit coupling, but that does not prove anything. So that's an interesting question. In this sense, probably the anti-commutation relation between these matrices have an essential role, I guess. And otherwise, we cannot get any minus factor. That's only I can say.
If you have phase, now you are sharing your equal by edge. If you have phase sharing, how much is modified?
That's a very different problem considered by Kugel-Komsky in old days. And in this case, everything is different, but the results looks a bit similar. Yeah. Sorry.
T2G orbitals, response spin-orbit coupling. You're saying that it has been considered by Kugel-Komsky?
In old days.
Oh.
Not old days, but in the previous work.
Remember if you can use maybe the lattice is for this alpha that you
Yeah.
So you show the list of 3D
Yes.
so here it's just
3D extensions in. It's all crazy lattices.